Hey guys, welcome back. So in the last video we learned how to find time complexity of a given recursive algorithm. Hope you have understood the concept. Now in this video let's take one more example of an recursive algorithm and try to find time complexity for that. So here as we can see we have a 1D array which is a sorted one. Now let's say our task is to find a number in this 1D array. So let's say we are trying to find if 110 is there in this array or not. Now to find a number in this array, the idea is simple. So we use a search called binary search to achieve our objective. Now what is binary search? Very simple. So what we do is, first of all we will start searching for the number from exact middle of this array. Now the next thing that we do is, if this value is equal to the value that we are looking for, which is 110 in this case, then we are good. We simply return this cell. Else, if this value is more than this value that we are looking for, in that case we go towards left. Or if the current value of this cell is less than the value that we are looking for, then we have to go to right. Now why do we do that? Because any number which is more than 60 will always be on right side, because this array is a sorted one. Similarly, any value less than 60 will always be on the left side of this array, because again this array is a sorted one. Now in our example we are looking for 110, which is more than 60. So of course it will be on right side of this array. So we move towards right. Now how do we move towards right? Again we do the same thing, that is, we take this sub array and find out the middle of this sub array. So the middle of this sub array is this cell over here. So again we do the same thing, that is, we compare this value with the value that we are looking for. If they are equal, we are done. We simply return this cell number. But in this case we are looking for 110 and the current value is 90. So we have to go towards right. So again we will take a sub array of this bigger array. Now the next sub array is only these two cells over here. Now again we have to find middle of this sub array. But the problem is, since the number of cells in this sub array is even number, that is 2 in this case, so we can either take this one or this one as a midpoint. So in this case I am assuming the first cell of this sub array as midpoint of this array. You can also take the second cell as the midpoint. Now since this is the midpoint of this sub array, we do the same thing, that is, we compare this value with 110. If they are equal, we simply return this cell, but they are not equal, so we have to go towards right, as 110 is more than 100. Now when we go to the right, we get this sub array with only one cell in it. Now since the value of this cell is equals to the value that we are looking for, we simply return this cell number. So you see that the number of comparison that we have done in case of a binary search is way less than the normal linear search. So here we have done one comparison here, then we compared 90, then we compared 100, and finally we got the value at 110. So basically we did 4 comparisons. Now if we would have done a linear search, we would have compared starting from here, keep going towards right and done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 comparisons. So you can see that we have done way more better when we have used a binary search. Now let's see how does the algorithm for this search looks like, and then we will try to find the time complexity of that algorithm. So the algorithm is simple. Name of the method is binary search. It takes as an input the number that we are trying to find, the array in which we are trying to find the number, the starting point of the array and the end of the array. Then we are checking if start equals to end. In that case, again we are checking if the value in the start cell equals to the number that we are looking for. Then we simply return the cell. Else we return an error message that the number does not exist in this array. Now when will this condition come? This condition will come when start equals end. That is, we have only one cell in the array. Like in our example, when we were over here, we saw we had only one cell, that is 110, and the value of 110 matched exactly with the number that we are trying to find, which was 110 again. So we returned the start, that is the cell number. In case, let's say if this value over here was 120, in that case this would not have matched with 110, so we would have said an error message that the number does not exist in the array, as this is the last cell in the array and there are no more cells to search for. So we will exit the method with an error message. Now this is our base condition. Now in case there are more than one cells in this array, then we find the midpoint of this array. So it says mid is equal to find mid. We give the array name, start and the end of the array. Now if mid is greater than find number, then we do a recursive call with the same number, same array. The only difference is start remains same but the end changes, so it becomes mid. In case if mid is less than the find number, then we have to go towards right. So we again do a recursive call and this time the start changes to mid and we go on till end. And in case if mid is equal to find number, then we are good. We simply return the cell number of mid. So here we see that we have two recursive calls over here, one call here and one call over here. And this is our base condition. Now let's see how to find the time complexity of this algorithm. So doing some comparison will take order of one time. Again doing some comparison, returning some value, returning an error message. All of these are constant time operation. Finding a midpoint is again a constant time operation. Again we have a comparison, constant time operation. This part we will come later. Here we have a comparison, is a constant time operation. This part we will again come little later. We are doing some comparison, returning some value. Again all of these are constant time operations. Now as we have learned in our previous example that in case of recursion, we have to assume some time complexity for the search, for the method, and then we have to go from there. So we have assumed that this algorithm takes t of n time. So when we come here, we see that we are doing a recursive call but on a smaller array size, and since we are doing it from start goes on till mid, that means we have divided the original array into exact half. So the time that will be taken to search will again become exact half of the original time. So let's say originally our array was having 100 elements in it and it was taking 10 seconds. Now since we have broken down this array into exact half, that is, now we have only 50 elements to do the searching on. So again the time taken will be half, that is 10 by 2. equals 5. So that's why we have put over here as t n by 2. Similarly, here we have divided the array into again equal to halves. So this will also take n by 2 time. Now if we add all of these time complexities, we get t of n is equal to order of 1 plus t of n by 2. Now why we are saying t of n by 2 and not 2 t n by 2? Because we have 2 times t n by 2. So adding them becomes 2 t n by 2. But again, since this is a constant term, we can avoid it. Fine. So now let's see how we can find the time complexity from this equation. So we have copied this equation from the previous slide and named it as equation 1. Now the next step is we need to have a base condition. So what is the base condition here? If t of 1 is equal to 1, that is, if the size of the array is equal to 1, that is, it has only one cell, in that case we can do the search operation in constant time. Now the next step was we have to found equation 2, which is nothing but same thing which is derived from equation 1. So we have found t n by 2 by replacing the value in this equation. So it comes out to be t n by 4 plus 1. Similarly, we will create one more equation, that is equation 3. This time we will find out t n by 4. How do we do that? We replace it in equation 2. So this gives us t n by 8 plus 1. So now that we have equation 1, equation 2, equation 3 and base condition, we are good to solve this equation over here. So let's see how we can do that. So our equation is t of n is equal to t n by 2 plus 1. Now the next step is we will replace the value of t n by 2 with equation number 2. So we have said t n by 4 plus 1 plus 1. And where did we get this t n by 4 plus 1? We got it from here. Now we will do some arithmetic. So it turns out to be t n by 4 plus 2. Now the next step is again we will replace the value of t n by 4 from equation number 3. So t n by 4 is equal to t n by 8 plus 1. So here we have put the same value t n by 8 plus 1 and this 2 comes here as it is. Now let's do some arithmetic. So it becomes t n by 8 plus 3. Now if we see, we have a pattern over here. This number over here increases by 1 in each step. Similarly, this value over here gets multiplied by 2 in each step. So here it was 2 to the power 1, here it is 2 to the power 2, 2 to the power 3 and so on. So now can we represent this equation in more generic format? Yes, we can do. So we have said t n by 2 to the power k plus k. Now what is k? K starts from 1 and it ranges from 1 till n. So now most of our work is done. Now all that we have to do is, if somehow we can eliminate this t function over here, we are all good. So how do we do that? Very simple. All that we have to do is, we have to insert some value of k over here so that this entire function over here gets reduced to t of 1. And since we already know the value of t of 1, we can simply replace the value from here. Now the task is how we can find the value of k. So n by 2 to the power k, for what value of k will this become 1? So answer is simple. All that we have to do is we put it as equals to 1. So n is equal to 2 to the power k and then k is equal to log of n. So if we replace the value of k with log n, this entire thing gets reduced to 1. So let's do that in the next step. So in the next step, we have replaced k with log n. So this over here function gets reduced to t of 1 and this k becomes log n. Now we already know that value of t of 1 is 1. We know it from our base condition. So we replace the same value over here. So it becomes 1 plus log n. Now 1 plus log n becomes log n because n is a constant and we can safely eliminate it. So this is how we find time complexity of any recursive algorithm. What we do is very simple. First of all, we find equation 1, then we find the base condition, then we find equation 2 which is basically derived from equation 1, then we find equation 3 which is derived again from equation 2, and then we do some arithmetic and we finally end up with our result. So this method is called back substitution. Now there is another method which is called as Master's theorem. Now Master theorem is not in the scope of this video series, so we are skipping it. But in case if you think that you need to learn it, please let us know and we will add that video as well. Now the question is that why we are not learning Master's theorem right now? Answer is simple. It is more of an academic thing to learn Master's theorem. When it comes to interview questions, most of our problems can very easily be solved using back substitution. So with that, we come to end of this topic, that is algorithm runtime complexity. So in this topic, we have learnt what is algorithm runtime complexity, why do we need to learn it, what are the various notations of runtime complexity. We also saw some of the examples or sample runtime complexities, and then we also learnt how to find runtime complexity of both iterative as well as recursive algorithm. Now all that we have skipped in this chapter is Master's theorem, and the reason I have already told. In case if you need to still learn it, please let me know. I will add that video as well. Fine. So we will end this video here. In the next video, we will start the next topic, that is array. Thanks for your time. See you in the next video.